I'm a software engineer at Goldsky, and I previously worked at Shopify as a production engineer. On my free time, I love being outdoors. I love hiking. This picture was 2 weeks ago. I was doing the Alpine Circuit Trail on the Canadian Rockies. That's kind of close from where I live. That's Lake O'Hara behind me. And yeah, with that introduction, let's get started. I work for Goldsky, which is a gold. It's a crypto-focused real-time data platform. So we allow blockchain developers to build Flink SQL pipelines, and we allow them to ingest real-time blockchain data and sync to whatever database they want. They can use webhooks. They can use a variety of syncs. They can transform the data with Flink SQL. And on the right there, you see one example of our customers. If you are familiar with blockchain, that's a feed of polymarket data. They allow people to bet on outcomes for events, like sport events, political events. And you can bet on an election, for example. You can bet on a game that you want to watch. And yeah. The agenda that I have for today, we're going to talk about the problem. We're going to get into a background of the technologies that we are going to use for solving that kind of problem. We're going to go into the technique itself, and then I'm going to talk about some of the highlights that we have in terms of results, some takeaways for the presentation, and then I'm going to have some time for questions. Starting with a definition of what I mean by bootstrap and backfill. I'm going to define it loosely as processing or reprocessing past data, and that includes missing information, late, incorrect information, and historical information in general. In this the typical problem is you have a really high volume of data that is typically larger than whatever high event you have. So like you can imagine, even like in the case for polymarket, an event like the election can cause a huge backlog of messages to suddenly show up. But compared to what we need to process for historical reasons, that tends to be not that big. So even with a highly partitioned input and lots of workers, and you can imagine a Kafka topic with terabytes of data, lots of partitions, a Flink job with lots of task managers, it can still take hours to backfill a pipeline. And we just want this to be a little bit quicker. We don't want our customers to be waiting for hours until they actually see results coming real time. So zooming in a little bit, because that was just part of the problem. If we inspect the pipelines that our customers build, we typically see a SQL that's somewhat like this. Like they select a few columns from the input, they use some functions, do some kind of transformations. Maybe they do a join, maybe they do a group by, maybe they don't. But almost always they include some kind of filter like this one, where it says address equals some value, contract equals some value. And they're typically only interested in a subset of the input. Like they never care about the entire blockchain because it has a bunch of data that does not pertain to their particular app. So what they want is the historical portion of the data that pertains to them plus the live data that pertains to them and nothing else. To give you a little bit more insight about how we store our data, our input topics are Kafka topics. They're typically really large. You can think of billions of rows, hundreds of gigabytes at least. And in contrast, the result of the backfill that they do is frequently under 100K rows, and very occasionally like it goes to like millions of rows and things like that. Especially like for the lowest, like the smaller developers that we work with, they tend not to have a lot of data, not a lot of historical data. They typically started their app a month ago or a few months ago, and they don't have lots of records yet. So to make a quick distinction about what we mean by a full backfill or a selective backfill, a full backfill is a case where you actually have to read the entire history of data. That's not what we're going to talk about here today. We are more so going to focus on the selective backfill, where we are interested in a subset of the data. And for that, the question that I'm asking is, can we actually do better? Like, can we do something that does not involve reading an entire Kafka topic with terabytes of data when the customer did not ask for that. Quick background, and we're going to compare logs and databases with respect to some aspects that are interesting for the presentation. First, distributed logs like Kafka allow you to have sequential access to the data. They are typically append-only, and you can change that a little bit, but they're typically append-only. They offer high throughput and low latency for both reads and writes. They typically do not allow you to index. Kafka allows you, for example, to index data by offsets or by timestamp, and that's pretty much it. But there's not much more than that typically. Databases, on the other hand, allow you to have random access to data. They're typically mutable. You can do whatever you want to the data. They're much more flexible in terms of the types of queries that you're allowed to do, and that tends to cost you a little bit more in terms of throughput and latency for both reads and writes. They also offer rich indexing, which in turn allow you to have like really fast queries for a variety of query patterns. Continuing the background into ClickHouse, which is kind of our choice of database for the problem. And I'm going to talk about why in a little bit. ClickHouse is a column-oriented database with strong compression. It allows fairly low latency writes in real time. We typically write to ClickHouse using Flink. You can just sync real-time data to it. It offers high throughput reads, and it allows you to overwrite data when you use engines like the replacing merging tree. So you can mutate history if you choose. And this is not consistent right away. There are some knobs that you can tune to materialize the results, to merge the results. And yeah, you have some control over that. You can also do a merge on read if you put some keywords in a query. A little bit more about ClickHouse. So ClickHouse is designed for OLAP, and it does surprisingly well in retrieving contiguous blocks of data, which is a very interesting aspect for the problem that we want to solve. On the picture that I have here in the slides, I'm showing a feature of ClickHouse called sparse index. And what it does is it allows us to use binary search to filter through sorted data. Our tables in ClickHouse are all sorted by a given sort key. So we typically set that based on the patterns that we think the customers are going to use to query the table. And what a sparse index does is, because the table is sorted, it essentially has one entry to a block in the table. ClickHouse divides the table in granules or blocks of data of 8,001 and 2 rows. And the first row of each granule is essentially a mark that they put in the index. And when you receive a query from the user, you can kind of do binary search based on the filter that they put and the marks in the index. And then you don't have to scan the whole table. That's why we can filter out subsets of a huge table really quickly. Another interesting feature of ClickHouse are projections, which are essentially fully managed materialized views. Don't confuse that with like SQL projections. That's like a different thing. But you can think of it as a streaming materialized view that you don't ever have to touch again once you set it up. So it's like really convenient. It does cost you a little bit more in terms of storage. So most times, in our case, we replicate tables entirely when we want to support different query patterns. And the advantage of using projections is that they are fully managed, and we set up them once, wait for them to backfill, and once that's done, they get updated in real time. And we don't ever have to think about it again. So in the picture, I just have like an example where you have an original table sorted by some sort order, and then we can create projections where we transform that original table in whatever way that we want. We can create aggregations on top of the table. We can drop columns, add columns, or change the sort order, which is what is most interesting for the problem that we have here. A few more reasons why we like ClickHouse. Very low storage cost, good compute cost, outstanding support. We have a channel with them, and whenever we have questions about how we can make things better or structure things better to better use their architecture, and their engine, they always come up with really good answers. ClickHouse is used throughout our company on very diverse use cases. We don't use just for backfills, we use it for billing, we use it for logging, and we have a really good relationship with the company. We've sometimes collaborated on things like CryptoHouse, which is a real-time database for blockchain data. If you are interested in crypto, go check that out. And one question that many people might have is like, could you use something else? The technique that I'm going to talk about holds no matter what database you choose. And if you go through the checklist that I have here and everything checks out, then you should be good. So if you check if the database provides random access, which all of them should offer of some kind, if they offer indexing, partitioning, or some form of file pruning, you should be good. If they offer overrides, you should be good with mutating history. And if they are cost-effective for the amount of data that you have, then you should be fine. Would Iceberg work for this? Most likely, yes. And if you already have Iceberg working in your organization, this would be one way to get started. One final piece of background that we need is Flink hybrid source. If you're not yet familiar with that, is essentially a source that was designed to bootstrap historical data. And what you can do with that is you can combine a number of bounded sources and read sequentially for them, and then lastly start reading unbounded source like Kafka. So you can imagine you can have a number of S3 bounded sources that represent the history of your topic, and then you can switch to a live Kafka stream after you go through each sequential historical source. And this was kind of conceived at a point where tiered storage was not really out there, and many people had data lakes with essentially archives of Kafka data, and they had just a smaller amount of the same data in Kafka in order to save costs. So let's get into the actual technique for lightning-fast backfills. Before, the scenario that we had was essentially we had a really large topic, lots of partitions, lots of data, and we had a customer come in and start filtering for input matches address 123. And then we got another customer doing the same thing with address 124 and so on, and we're having like 1,000 of these Flink pipelines, essentially reading the same input, throwing a bunch of records out, only to get like 100K records that they actually care about. What we're going to do with this technique is essentially decoupling the historical piece of the data from the real-time piece. So we're going to use ClickHouse as the bounded source for the history, and we're going to do a smooth switch over to Kafka, the real-time source. The really important part here is that the Flink job itself is not going to do the filtering. We're going to push the filter down to ClickHouse so that we only actually stream the 100K records into the pipeline and not the whole history. So a really brief overview of what it looks like from the top. In blue here, we have what we call a reader pipeline, which is essentially the customer pipeline that's going to be responsible for reading the data using the hybrid source. And you could have thousands of them at any given time. Doesn't really matter. And at the bottom here in purple, we have what we call a writer pipeline, which is essentially a pipeline that we use to archive the data from the Kafka topic into ClickHouse and to generate something that we can use to blend the historical portion with the live Kafka stream later on. You have the Kafka ecosystem represented here on the right, just so that we can actually read the data and get the schemas for it, and the ClickHouse ecosystem at the end with a table that we use to track offsets and the tables that actually contain the archive data. Zooming in a little bit on the writer side. So I told you that the writer pipeline is responsible for archiving the data that we have in Kafka into ClickHouse. And how does that actually happen is we have a Flink pipeline that is reading data from Kafka, is doing some data type conversions in order to get data into a more user-friendly shape into ClickHouse. Reason being, we use the data in ClickHouse for more than backfills. We have people doing quality analysis, doing analytics on top of that data, and it helps if they can deal with data types that are more user-friendly. You can think of, instead of using Unix epoch timestamps, they can use actual ClickHouse data types, and in that way they get nicer queries, use datetime, for example. After that data type conversion, we pass the data to the ClickHouse writer, a Flink sync that writes to ClickHouse, essentially, and we start writing to the main archive table for that topic, like the mirrored version of the topic. We can also optionally create projections or extra indexes on the ClickHouse table, and we do that on a case-by-case basis, depending on whether we think users could benefit a lot from that extra query pattern and whether the extra storage cost that we would incur would be good for that. One interesting thing is that as we write to the ClickHouse table and we archive the data, we also have to track progress of how fresh the archive is. We do that like for every batch of rows that we write to ClickHouse. We also keep track of the Kafka offsets in the source topic so that we know at any given point how fresh the archive is, and that's going to help us to initialize the offsets for the hybrid source on the other side when you start actually reading data. So the reader pipeline starts essentially by reading from the offsets table in ClickHouse. Again, that was kept update by the writer, and the reader retrieves those offsets, starts the offsets initializer, which passes that offsets to the Kafka source. And after it does that, it runs some checks on the filter that the user passed in. So in the examples I had before, we had the user passing a filter address equals 123, and we treat that essentially as a SQL expression. The user can enter anything, put any columns, any functions that are valid, both in ClickHouse SQL and in Flink SQL, and we execute those. And one component that we had to be able to kind of make that a little bit safer was this filter processor that I have here in the diagram. And its responsibility is essentially to validate that the filter that the user is passing in is valid, and we do that ahead of time to avoid having filters that are just broken or that we know for sure are going to perform poorly. So we have this component where on the performance side, for example, we check whether the columns that the user put in the filter are actually backed by the sorting order that we have in ClickHouse, or by the projections, or by the indexes. And if that's not the case, then we have the option to add more projections or add indexes for that particular table. Some other things that we have to do here is before we actually start reading data from ClickHouse is to initialize a data type converter that's going to convert data back from the user-friendly ClickHouse schema that we created to a schema that's compatible with the source of truth that we have in Kafka. So we initialize that converter, and then we start the actual process of reading data from ClickHouse. We have an internal Flink ClickHouse connector that's heavily based on the open source one, and we made a bunch of modifications, including this paginated input format, which helps us with paginating through really large result sets. For the cases where we need to return like millions of rows, we paginate through them so that we can actually avoid timeouts and just like have like a more reasonably sized payload. And that paginated input format forwards the data to the ClickHouse source, passes through the data type conversion, and then it goes through the rest of the pipeline. And as the ClickHouse source is reading data, once it exhausts all the pages, it sends a signal to the hybrid source saying, I'm done, you can go on to the next source. And then the hybrid source switches to the Kafka source, which has already been initialized with the offsets that match the current freshness of the archive. So we do like a smooth switch over right after the point where the archive finished. And yeah, talking about some of the result highlights, Backfill used to take hours or days, and now it takes from seconds to minutes. Backfilling time increases with the size of the result set returned by ClickHouse, which is kind of expected. In the case where we have to return like millions of records, we paginate for them. It takes a couple more seconds to return, as opposed to when we had a really small result set. A user filter can still be too expensive for ClickHouse to execute and result in poor performance. And in that case, we have the option to add indexes and projections to better support it, like I said. Some takeaways. Backfills don't have to take forever. We also don't have to spin up 20x more workers to get it done. I've done that a lot in the past, but once you see thousands of people doing the same and you realize how much waste is going on, you try to think of something else to avoid it. And by leveraging random access to past data, we can process only the subsets of data that matter. We don't actually have to go through everything. And our implementation of that design uses Flink hybrid source, Kafka, and ClickHouse to go from history to real time in the time that it takes to drink a cup of coffee. That's it. That's what I have for today. I'll take any questions you guys might have.